All right, yeah, so these are just tricks, but they sort of represent a lot of power, sort of examples of a powerful technique we're going to use, which is taking problems about integers and reducing them to problems over small sets of numbers, right? Integers modulo something. And I was introduced to this idea many years ago. I was a geek, go figure, when I was a kid, and I loved math and I loved prime numbers. We're going to talk about prime numbers in a bit. Numbers that aren't divisible by anything except themselves and 1. So 5 and 17 and 101 and so on and so forth. And somewhere someone told me that there was no known way to generate prime numbers, and so I was like, well, I'm going to figure that out, you know. So I started coming up with all these crazy algorithms for generating prime numbers, and they would work for the first few numbers, and then the numbers would get so big that I couldn't tell if they were prime or not, right? So I was like, well, it looks prime, so I probably got something here, so I'm going to be famous in a few days, you know. So I found a mathematician. His name was John Selfridge. He'd written a book that I was studying. He was a math professor at the University of Illinois, I believe. And I wrote him a letter. I think I was like 10 or 12 years old at the time. And told him, you know, I believe I've come up with a formula for generating prime numbers and blah, 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 blah. And he wrote me back this nice long letter, right, even though I was just a kid. And he told me, you know, that the number that I had sent him, that was the first number I couldn't test, in fact, is not prime. It's actually divisible by this, and when you divide it by this, you get that. And he showed me how he had found that out, and he had done it using modular arithmetic. And it was a little piece of paper that came out of an adding machine, you know, add, subtract, multiply kind of thing. This is the paper tape from it. And he had basically done modular arithmetic, and he'd figured out that it was divisible by 23 without using a computer. There were no calculators at the time, without using any kind of major machinery, by using one of these kinds of tricks. And that was magical to me, right? And so I just found a bigger number that didn't work on, and I'm like, no, it must be prime. I never found my formula. But anyway, so you can answer questions about seemingly big numbers sometimes by doing very little work if you move over to this equivalent modular system. Now, you can't answer all questions, right, because 23 is not the same thing as 1,023, right? But if you're interested in remainders when you divide by 100, right, you may as well just be using 23 and throw away the extra stuff. So when we think about modular arithmetic, it ties us into prime numbers a number of ways. One of them is this. Let's think about multiplication, and let's think about multiplication modulo 5. So I'm going to label this table x5. So this means multiplication mod 5. And the only numbers I have in this universe are 0 through 4. And I'm going to make a multiplication table. That's how we learn multiplication in school, right? We just write down all the products. So 0 times anything will be 0. 1 times anything will just be itself. 2 times anything, well, I'm just going to double. This is going to be 0, this is going to be 2, this is going to be 4. This will be 6, which rolls over to 1. And this will be 8, which rolls over to 3. And 3, this will be 0, 3, 1, 4, and 2. And 4, this will be 0, 4, 3, 2, 1. And you can test those. 4 times 4 is 16. It's one more than a multiple of 5, and so on. All right, let's do that again, but let's do it modulo 6. So the zeros are easy, the ones are easy, the 2s aren't too bad. 2 times 3 is 6, that's 0. 2 times 4 is 8, that's 2 more than a multiple of 6. 2 times 5 is 10, that's 4 more than a multiple of 6. So that's what multiplication looks like mod 5. And the first row and the first column are never particularly interesting because they're just a bunch of zeros, so let's get rid of those. And let's just look at this middle piece. And other than the different numbers themselves, because we're multiplying modulo something different, what differences do you notice in general between this set of numbers and that set of numbers? What sorts of things jump out besides there's more numbers here? Or what's similar between them? Yeah, so the bottom row seems to be just counting backwards. That happens here. And the rightmost column counts backwards. That happens here also. And that works because this last number is actually congruent to -1. And -1, we're kind of counting backwards if we go up by -1 more each time. So what about a difference between the two? There's something in the table on the right that's missing from the one on the left. Besides 5, because 5 is just too big to be in the left. But yeah, you're right. There's zeros in the one on the right. Right here. Right here. There's no zeros over here. Okay, if we make a multiplication table with just plain whole numbers, 1, 2, 3, 4, 5, on up to, I don't know, 12 or 20, whatever your multiplication table in school says, do we find any zeros in there other than, you know, the first row and the first column? All right, you never get zeros when you multiply two things together unless one of them is 0. Yeah?
So would that mean for every prime number it wouldn't have any zeros in the table?
Yeah. So this is weird, right? We've got 2 times 3 basically giving us 0. Well, what's the rule that we learn when we're doing algebra? If a times b equals 0, either this is 0 or that is 0. That's how we solve equations in algebra. We say, oh, the product is 0, one of them has to be 0, and now we have two sub-problems. Either find where that makes it 0 or that's 0. But here we've got two things that are not 0, but their product is. That's weird, right? This thing doesn't work modulo 6. It's a very different type of mathematics. And it turns out if we have this situation where two non-zero things can multiply to give you 0, we have a hard time doing division. Division works well as long as we know that the only time things multiply to 0 is if one of them is 0. So if we're working mod 5, we can actually define division. We could say 3 divided by 2 is equal to 4, because 4 times 2 is equal to 3. But if we try to take 0 divided by 3, we might get 2, we might get 0. And if we wanted 1 divided by 4, there's nothing we can multiply 4 by that gives us 1. There's nothing we can multiply 4 by that gives us 2. There's nothing we can multiply 3 by that gives us 2. So not everything is divisible by anything else. But over here, we can divide every non-zero number by any non-zero number. We can find a multiple of 3 that's equal to 1, 2, 3, or 4. We can find a multiple of 4 that's equal to 1, 2, 3, or 4. And the difference is that 5 is prime and 6 is not prime. It's what we call a composite. So doing modular arithmetic over a prime number is special. It's more powerful because mathematically what we're talking about is something called a field. And fields are a special type of algebraic object. One that we can do division, basically. So we can always add, subtract, and multiply. We can only divide if we've got prime number modulus. Okay, so why are primes interesting? Anybody here from the East Coast? Besides me? Alright, so you may never have heard this. Anybody ever heard that?
Kind of like crickets?
Yeah. So that's a cicada. You're right. So cicadas are these beautiful or ugly, depending on your perspective, bugs. They're like about that big. They're harmless if you're a person or a large creature. They're not so harmless if you're a plant. And they usually have these like iridescent eyeballs that just like all these different colors of the rainbow and tons of structure to them. And the cool thing about cicadas is they pop up every 17 years on the East Coast. And they live for a few weeks. They go up in a tree at some point and they drop down in the ground and burrow into the ground, and then they hang out in the ground for 17 years, the larvae. And 17 years later, they dig their way out of the ground, and they molt their skin, and they come in this, full-grown form, and they climb up in trees, and they make noise. And they all do this together every 17 years. So the last 17-year brood was, I think, 2 years ago on the East Coast. And if you ever have a chance to be on the East Coast when it's one of these 17-year cycles kicking in, you will definitely know it, because cicadas are everywhere. They cover the road. You come out in the morning, you brush them off your car. I mean, the numbers are unbelievable.
Do they know why 17?
No.
It's a prime number.
But it is a prime number. And if you go out into the woods while this brood is out, it's deafening. Walk deep into the woods and you're just surrounded by this, and it's like painfully loud. Just a phenomenal number of these things. So every 17 years this happens. Well, there's another brood that also comes out every 13 years, which is also a prime number, 17 and 13. And there's theories as to why this is. But one of the theories is because 17 and 13 are prime, very, very infrequently they're going to come out of the ground at the same time. Every 13 times 17 years, so every 200 years or so, they'll both appear at the same season. Other than that, they're going to come out at different seasons, and there's less competition. So that may be, a cool theory, or it may be reality, or who knows. But prime numbers pop up in all sorts of places. Nature being one of them. And so people have studied prime numbers for a long time. And, I'm a prime number geek. So my Steam name is Prime Minister 37, because I like primes. So primes were studied, at least back to the Greeks. Yeah?
Are we going to talk about the Mandelbrot set?
I'm sure it's related to primes. I wasn't planning to talk about it.
Because it reminded me of the Beatles.
Yeah. Yeah, Mandelbrot sets and fractals and all that stuff. That's all would be totally fair game for this course. Yeah, maybe we'll talk about it. How many people here? Let me do a YouTube shout out. How many people here have looked at this channel, Number File?
Oh, yeah.
Okay, that's an awesome channel. It's just all these weird things about numbers. that, like the 10958 problem. Stuff that's like, you know, pretty easy to understand, but 10 minutes into the video, your brain is just blown apart, right? And this whole channel is just filled with this stuff, so. Riemann hypothesis, maybe not so easy to understand, but yeah, and then the sum of the positive integers is -1/12. That's more Riemann hypothesis. Take a look at this if you like. It's Mandelbrot said it's a lot of really fun mathematics. You know I got to see monkeys and coconuts, right? So prime numbers, right? At least back to the Greeks. So a number, a positive number n is prime if its only divisors are 1 and n. Only positive divisors. And 1 is not prime, even though it fits that definition. So you might say a number n bigger than or equal to 2 is prime if its only divisors are 1 and n. And so 2 is prime, it's only divisible by 1 and 2. 3 is only divisible by 1 and 3. 4 is not prime because it can be written as 2 times 2, so it's divisible by 2. 5 is prime, 6 is 2 times 3, 7 is prime, 11, 13, 17, 19, and on they go. And so there's a relatively simple way of cranking out prime numbers. It's not quite generating them, but there's a way of listing prime numbers. How far is he going to go? We'll stop at 24. So there's the numbers 1 through 24. Okay, how do we find the prime numbers? We're going to circle the primes. So we're going to circle the first number, which is 2, and then we're going to cross out every second number after that. Alright, we're going to circle the first number that's not marked, and we're going to cross out, in this case, every third number after that. So 6, 9, 12, 15, 18, 21, 24. Next number that's not marked is 5, and we'll cross out every fifth number. So 10, 15, 20, and I would do 25 if I was going. Next number that's not marked is 7, cross out 14 and 21. Next number is 11, we'll cross out 22 and 33. Next number is 13, and we'll cross out 26 and so on. And 17, we cross out 34, 19 and 38. And we've circled all the prime numbers up to 24. So that's called the sieve of Eratosthenes, which I probably spelled wrong, sorry, whoever you were. But that's one way to generate primes.
You wrote it so we couldn't read it, so we can't tell whether
You like that trick? But try it at home. It's NES. Right? And it makes sense because when you cross out every fifth number, you're taking out all the things that are divisible by 5. When you cross out every seventh, you're taking out all the numbers divisible by 7. If something hasn't been crossed out, it's not divisible by any of the numbers below it. So that leaves you with prime numbers. But that's not really practical for telling if something's prime or not. Because if you want to know if a number in the billions is prime, you don't want to write out a billion numbers and start crossing them out. So is 1001 prime? Well, to me that looks like a prime number. But how do we know if it's divisible by anything other than 1 in itself? So how will we tell? If you've done 121, you've probably already done this. But desert island, nothing to do. Got whiteboard somehow and some markers. How would you tell if 1001 was prime?
Start dividing by 100.
Just start dividing it by things and see if anything divides it evenly.
Take the square root first.
Yeah, so divide by 2, divide by 3, divide by 4, all the way up to 1,000. If it's not divisible by any of those, then it's prime. And so Randy just said take the square root first. Why?
Because the number just greater than the square root is the largest possible number.
Mm-hmm.
You wouldn't have to go all the way up to 1,000.
Right. So if 1001 divided by A is equal to B, one of these has to be bigger than or equal to the square root. One of them has to be less than or equal to. If they're both bigger than the square root, then their product is bigger than 1001. So we only have to test factors up to and including the square root of our number. So we only have to go up to probably 11. Can we do it any quicker than that?
You can only divide by prime numbers.
We only have to divide it by the prime numbers. Because if it's divisible by 6, since 6 is divisible by 3, it would have been divisible by 3. If it were divisible by 9, it would again be divisible by 3. If it's equal to 9 times something, that's 3 times 3 times something, it's divisible by 3. So it turns out we only have to divide it by 2, 3, 5, 7, and 11. And we know 1001 is not divisible by 2 because it's not even. It's not divisible by 3 because the digits don't add up to 3. It's not divisible by 5 because it's not ending in a 0 or a 5. But it is divisible by 7. And 143 turns out to be divisible by 11. And in fact, if we did the even-odd trick, the sum of the even digits of 1001 is 1, the sum of the odd digits of 1001 is 1, difference is 0, we'd know 1001 is divisible by 11. So 1001 is not prime. But 101 is. So we can write a program to check to see if a number is prime by just dividing by all the prime numbers, or maybe all the numbers below its square root, starting with 2.
Is that going to be our next assignment?
That would be a good assignment, actually. I mean, you usually do this in 121, or in 120 in MATLAB. I think you do this. But yeah, we should play with prime numbers. In fact, we will play with prime numbers. So this was how I got into computer science, because I was like 15, I think, and I was still looking for formulas, and I was cranking out bigger numbers, and I was using little tricks to tell it, and I got, a big number, and I gave it to my dad, and told him what I was trying to do, and he's like, well, someone at work might be able to answer this. He worked at IBM. So he took it into IBM, and he came home that day with a really shiny piece of paper with these large, bold-faced black characters on it. It was made by a Tektronix printer, really old school. And it had, big long number equals this times that. And I was like, wow, that's cool. So I tweaked my algorithm, came with a new number the next day, took that in, gave it to his friend at work, came home. But this time, not only did he show me what it was divisible by, but there were like 5 lines of literally Greek characters, deltas and epsilons and iotas and things like that on this page. And I'm like, what's this? And my dad's like, I don't know, he said this was the program he used. So it was a language called APL. It's an old language from the 60s. And it has no lowercase letters. It has uppercase letters and it has Greek letters. And all the functions are represented by Greek characters. And I took this into my friends in school, and we stared at it, and we studied it, and we speculated, and we figured out what it did. And this is what it did. It divided the number by every integer between 2 and the square root of that number. And it was like this epiphany to me, like there's no magic. You don't have to like have the magic prime number dust that you sprinkle on your machine and it tells you if it's a prime number. It's doing what you would do yourself. It's just doing it a lot faster. And that's when I fell in love with computers. So this is a brute force approach, right? But it works. Computers are really good for brute force things because they don't make mistakes usually, and they work effortlessly, and they don't complain usually. And you know, they'll get you the answer eventually. So if we want to test primes, we can do it with a computer, but only up to a point. Because if you're trying to test a prime up to 1 billion, its square root is, you know, a 4 or 5 digit number. Well, that's not too bad. If you want to test a number with 100 digits to see if it's prime, well, there's 10 to the 50th numbers you're going to have to divide it by. That's a lot. All right, 10 to the 50th. So that's where things become intractable. So we need to use some knowledge of math to answer some of these questions. So I'm not going to go into super crazy stuff right now. Let me just give you a few weird things. So there's things called Mersenne primes. Mersenne was a mathematician. So we know 2 is a prime, right? It turns out if you take 2 squared minus 1, what do you get? 2 squared is 4. That's 3. That's also a prime. Okay, the next prime is 3. 2 to the 3 minus 1, that's 8 minus 1 is 7. Hey, that's prime 2. 5 is a prime. 2 to the 5th minus 1 is 32. Minus 1 is 31. That's a prime 2. So we're on a roll here. 7 is a prime. 2 to the 7th minus 1 is 127. Guess what? That's a prime 2. And if you do this with things that aren't primes, like 2 to the 6th minus 1, that's 64 minus 1 is 63. That's not prime. It's divisible by 3. So the first few times that you do this, it starts to look like if you take a prime number to begin with, raise 2 to that and subtract 1, you get a prime. And it turns out that's often the case, but not always. So when that turns out to be the case, you get what's called a Mersenne prime. And it turns out pretty quickly, numbers in this form stop being prime. But here's the first few. So 2 to the 3rd minus 1, that was known 430 BC, same with 2 to the 3rd. 2 to the 5th was 300 BC, 2 to the 7th, and then there's a big jump. 2 to the 13th minus 1, 8,191, that's prime also. 2 to the 11th minus 1, not prime. It's got factors. But for the prime number 13, you do get a prime. Whoever did that didn't want to be known, I guess. And then in the 1500s, 2 to the 13th, 2 to the 17th, 2 to the 19th minus 1 were confirmed. And the method used was trial division. Let's divide by 2, 3, 5, 7, just keep dividing, right? Desert island approach. And then we jump up to the 1700s, and Euler, 2 to the 31st minus 1 is prime. Trial division with modular restriction. So this is starting to use some of these tricks that we have when we do modular arithmetic. And then we jump ahead 111 years to 2 to the 61st minus 1 is prime. It's a big number, and it's using something called Lucas sequences. So now we're getting into some heavier math. So Lucas Lemur, a pair of mathematicians that developed different facts about Mersenne primes that we can use to test if one of these numbers is prime without dividing by every possible divisor, because it's a much smaller set. And this is the approach that computers take today when they want to know if a Mersenne prime, if a Mersenne number is prime or not. So 1900s to the 89th to the 107th. This one was Lucas. In 1876, he found 2 to the 127th. And then we jump up to where computers start coming in, and these are computers, right? So that's the SWAC. You had to wear a tie to use it. So 2 to the 521st and so on. And things look good through the 60s, and we get into the 70s, and there's a good old IBM 360, one of the original big irons. CDC, Seymour Cray's company, Control Data Corporation, and then the Cray One, Seymour Cray spin-off companies. How many people here have seen a Cray computer before? Right, Crays are works of art. These things, they had, you know, see-through panels with cooling going, and if you ever done PC modding, right? Seymour Cray was the original modder. Beautiful machines. If you watch the movie Sneakers, there's a Cray in there. And they've got, you know, benches you can sit on around them and stuff like that. And so this is going well, it goes into the 90s, and then all of a sudden we start seeing 90 megahertz Pentium, 100 megahertz Pentium, 200 megahertz Pentium, 800 megahertz Athlon T-Bird, right? These are people's home PCs. And they're credited to something called Gimps. Gimps is the Great Internet Mersenne Prime Search. And it was a system where you could download this software, and when you weren't using your machine, instead of doing a screensaver that says Windows and floats around, it would search for prime numbers. And it would talk to the server, we get a new Mersenne number to test, and it would start using the Lucas-Lehmer algorithm to see whether or not it was prime. And when it finished, it would report back composite or prime. And these are people whose PCs discovered new Mersenne primes. And that's been the gig for, you know, 1.5 decades now. So about a year ago, the largest prime was discovered, and it's 2 to the 82,589,933 minus 1 is a prime number. And this is how many digits it has, so 24 million digits. And it was discovered by this person on his Intel Core i5.
Well, there has to be some significant reason why a lot of people think that this is a good thing to do.
Yeah.
Besides just being fascinating.
Yeah, there doesn't have to be a good reason, but there probably is.
Yeah,
There doesn't have to be a good reason for people to be doing it, right?
Well, yeah.
But primes are so simple to understand, and there are so many unknowns about them, right? That it feels like you're prying back a cover on something, and the more you can pry that cover back, the better glimpse you can get of whatever's behind there.
Do these results have any implications for the cryptography of the
So some of these results have implication for cryptography, although you would not use a Mersenne prime as one of your unknown primes because there's only 51 Mersenne primes. But cryptography relies on being able to discover large primes, right, hundreds of digits, that nobody knows about, basically. Cryptography works because you can take 2 large primes and multiply it, and you can show the world the product, and they can't figure out what the 2 primes were. That's basically how one-way cryptography, how public key cryptography works. But primes, if you want to read about Riemann hypothesis or the zeta function for some light reading on the weekend, those all come out of prime number theory, and it's just fascinating where this stuff goes. It's pretty crazy. The other thing, just to mention, along with Gimps, there's also this thing called SETI at home. If you want to search for extraterrestrial intelligence instead of prime numbers, same setup. Download the SETI at home software, and when your system's idle, it'll go out to a central server, and it'll pull down a chunk of data that was recorded by radio telescopes, and it'll look for signatures of intelligence. And if it finds any, it'll let the server know, and then people will go and look at it more closely. And so there's this worldwide effort going on just using spare cycles on your laptop to analyze incoming signals for signs of intelligence. Markers related to hydrogen and oxygen, I think, is what they're using.
What's that called?
SETI at home, so SETI, search for extraterrestrial intelligence.
So what about the Lucas-Lehman theorem? Is that something you're going to teach?
We're not going to go into that, no. I barely understand that myself, and that was a long time ago. All right, so have a great weekend. I'm doing a talk on Git in 5 minutes for the engineering club if anybody wants more Git info, but it's going to be a rehash of what we've done in 224 already. But I'll be in there.